50 years. Pretty amazing stuff. You want me to just go ahead and wait on in here? Or
I guess
I'll wait till the appointed hour. Yeah, that's okay, cool. Well, this is good. I'm Ward Silver. My hand call is N0AX. I graduated in 1978 and then hung around for another year doing some fun stuff. And, moved out to the West Coast, worked in Seattle for 27 years, and turned around and came back. Baseball team wins, and you can grow right to me. So that's kind of cool. Anyway, been working with W0 guys, and spent a lot of hours down in the basement of the Raleigh building back in the day. We had the only dime Coke machine on campus for a long time. I didn't realize that was as good as it was going to get. You know, you had an air-conditioned radio club, the dime Coke machine. You could climb up the coax bundle to get to the antennas at all hours. Did I just say that? And the student union was 50 yards away. So it's been all downhill from here. I think I spent 600 hours just on the air 1 year. I was totaling up contests and all that kind of stuff. And so I used to joke that I got my BS EEE here, managed to graduate anyway, and had a wonderful time. So I'm really glad to kind of be back and give a presentation to the EEE guys. Let's see, I've been a ham since I was 17, and that can be a good thing. That can be a bad thing when you come to college. We came sort of knowing a little bit about electronics and some electricity, and we'd taken apart televisions, and I still have some parts from those days, and some tools that I bought when I was in junior high to take apart televisions, still have them stuff. We were very practical, right? The circuits, hook up things, cables, whatnot, and made contacts with them in radios. And the professors had to sort of drag us up from the basement to a more abstract understanding of what it was that we're doing. We kind of understood what single sideband was, and that you had to tune it in a certain way, and you couldn't use the wrong sideband or everything was scrambled. And then you got the math, and you said, oh, I get it. That's what it sounds like. Here's what the math is all about. Nowadays, it's almost completely different. And people that come to electrical engineering tend to have a more abstract network sort of approach to all this, and you have to help them dig down into the physical layer. I used to teach at Seattle University for a few years, and I would do the labs. Professors hate doing labs, right? I like them. So you get these big books, and you have to carry all the lab books and stuff. My students used to joke that I would calibrate my red pen, and sort of their grade depended on how much red ink I would take out of the pen when grading their lab book. But I would get a lot of students who came to electrical engineering without the kind of practical, hands-on, hamster type of background. And so it was a very enlightening process for me. So anyway, I'm glad to work with students now. I write I edit the big ARL handbook, the 1,400-page monster, and the antenna book, and all 3 license manuals. Take your licensing exam and use the ARL stuff. It's my fault, okay? So I've written for QST and a bunch of other stuff, and all this writing business would really amaze my high school English teachers that I make my living writing now, as opposed to being an electrical geek. So I think the appointed hour is upon us. I'll go ahead and launch right into this. This is a typical talk. I find that a lot of hams and even electrical engineers approach this topic of impedance matching as kind of a mystery. It's like a thing that we have to do. I've got some little rituals and dances that I do to make this happen. It seems to work. It seems to help. I know I've got to have this piece in here, but what is really going on? So I'm not going to get in deep into the theory here. This is kind of a cookbook overview, here's what it is, here's what it's for, here's some techniques, with the typical audience for this talk being hamsters. Here we go. Okay, so why do you want to impedance match in the first place? Let's back up a little bit and talk about what impedance is. Impedance is the ratio of voltage to current. It's how hard you push divided by how much you get. That's basically it. And you all use impedance matchers every day, every time you get in your car and you drive along the street and you hear your engine go like that. You're using an impedance matcher. Your impedance, it's a vehicle transmission, is nothing more than an impedance matcher. Okay? The mechanical analogy is voltage is sort of like torque. That's how much you twist. And speed is how much you get. So speed is like current. So mechanically, a transmission or a gearbox is very much like an electrical impedance matcher. That's all it is. It's a mechanical impedance matcher. It's trying to transfer power from the engine to the wheels at an impedance that the engine likes. Your engine likes to be in that 1500, 2000, 2500 RPM type of environment. That's where its torque curve likes to live. That's the impedance it likes. So what you want to do is transfer power. Let your engine run at an impedance it likes, which is sort of like a transmitter wants to run at 50 ohms. And you're going to change the combination of torque and rate of rotation while losing as little power as possible. Your transmission will heat up a little bit. You'll lose a few percent of those horsepower going through it. Just like in an impedance matching box or network electrically, you'll lose a few dB, tenths of a dB in this process. So all you're trying to do is transfer power from one combination of torque, rate of rotation, or voltage and current to another ratio of voltage and current, while losing as little power as possible. Typically, you impedance match so that you can get the maximum amount of power out of your generator into whatever load that you're trying to get to. You want to reduce feed line loss. That's another important reason that hams do impedance matching, is your antenna is out there. It's going to have some feed point impedance, but you have no control all over the place. So you would like to match that to your feed line loss, so that when the power goes up the feed line and it gets to the load, it doesn't bounce back toward the generator. If it sees a 50 ohm load, if you've got 50 ohm coax, it goes our 50 ohm output. Okay. And don't hesitate to ask questions. What are the consequences of not matching? Oh my gosh. Well, you get elevated SWR, standing wave ratio, in a feed line. And you get that power bouncing back and forth. Well, most of it's still going to come out the load, but every time it makes a trip through that feed line, some of it gets converted to heat. So we typically don't want to do that. More trips through the line, more reflected waves, well, that burns up some of your power as heat. It also raises the peak voltage in the line. You get these standing waves where the voltage is high along the line, and the higher the voltage, the higher your dielectric loss in the insulation between the center conductor and the outer shield. Or if you have a parallel line, you're going to get more loss in that dielectric between the conductors. It also raises the peak current. You can measure SWR as the voltage SWR, or you can measure it as the current SWR. And just as voltage goes up when you have a high SWR or elevated SWR, then you also get current that goes up. In current, you get I²R losses in that very thin coating of copper on the surface of your conductors. Most of the loss at high frequencies, HF and below, is I²R loss. So you want to minimize these peaks of current in your line. As you go up in frequency, more and more of the loss becomes dielectric. So another reason is unhappy transmitters tend to dial back their power. Okay, how many people drive a stick? Oh, a few left. Okay, very good. You put it in third gear by mistake, and you try to accelerate off the stop sign. You're gonna go, and it's gonna kill your engine. Your transmitter is not happy. Your impedance was too high. Okay, so same thing with RF transmitters. They don't like elevated SWR. They don't like elevated SWR because peak voltage and current. And we have solid state amplifiers now. A solid state transistor is always 1/2 cycle away from utter destruction. Okay, so what you want to do is minimize the amount of voltage and current that it is subjected to. And these new pallet things, I'm sure you've seen the videos where the guy's putting the screwdriver right across the output and sparks are flying all over the place. Well, it's got a protective circuit in there that removes power and dials back the power when it sees peak voltage and current that are too high for your transmitting device. So they dial back their power. That may not destroy them right away, but definitely once you start getting your SWR up over about 2-to-1, maybe 3-to-1 for some transmitters, you see an amateur transmitter starts to dial its power back. This is not so much a commercial thing, it's an amateur thing because we use so many different frequencies and so many different antennas that the manufacturers would be forever repairing our output amplifier devices if we did not have some kind of way to reduce power to reduce its voltage and current. Elevated SWR can also reduce your receive sensitivity, particularly at VHF and up, where you don't have an effective match into your coaxial cable, and once you lose a received signal, you can't get it back. It's gone. It's heat. You can't preamp your way out of this. So what you want to do is make sure you've got a good match to your feed line at the antenna and for any preamps. Also, it reduces your SWR bandwidth. Typically, you get a nice curve across one of the amateur bands. It'll have low SWR in the middle and higher at each end. Well, the higher the SWR is in that feed line, that raises that whole curve. So those 2-to-1, 3-to-1 points, wherever your transmitter starts dialing back, are closer together in frequency. So it can reduce what's called the SWR bandwidth. Also, it does not increase RFI noise or pickup. SWR has nothing to do with interference or noise pickup. There are lots of other mechanisms out there that are often found in conjunction with elevated SWR. But elevated SWR does not by itself cause radio frequency interference or noise to be picked up by your antenna or the feed line. There are whole books about RFI and EMC and stuff like that. But SWR is not the problem. SWR does not change the antenna pattern. Your feed point impedance is what it is. I just wrote an article for QST talking about the dipole antenna and where do you put that feed point. How many musical instrument people do I have here tonight? Any guitar players? Okay, you can pluck that string in the middle and you can pluck it at the end, pluck it all the way up and back, and all that does is pick a different impedance point on the string. It doesn't change the string's fundamental frequency, it just changes the way you get power into and out of that string. And it's the same way with an antenna. The SWR may go up and down, but the physics of what's going on when electrons finally get to moving in the antenna does not change. It doesn't change your pattern. It does not cause bad breath or embarrassment. All right, this is a great video if you've never seen it before. I've shown this to graduate level students and they are rapt with attention. Go to YouTube and look up the AT&T archives and this video, similarities and wave behavior. And it's a little bit, it's black and white, the guy's got a suit and a tie on, it's a little bit of a Mr. Wizardy kind of feel. It's a marvelous presentation. It's Dr. Joseph Shive, S-H-I-V-E, and he had invented a wonderful thing called the wave machine. And it's basically a long, stiff wire with little bars soldered to it, little rectangular bars. And everything's painted black except the end of the bars, which are white. And so he sets this thing up on these little standoffs along the table, and he wiggles it, and you can see the wave moving down. And then he shows you reflection and impedance matching and speed of propagation and all these things. And he works through very simple math to explain what SWR is, what matching is, what velocity propagation is. Wonderful, wonderful video. It's 40 minutes long. It should be your very next topic of a meeting. Anyway, good stuff. And there's a lot of good things in the AT&T archives, including a wonderful presentation on how the old mechanical relay phone switches used to work. So anyway, good stuff. Here's a question that comes up a lot associated with impedance matching. Where did 50 ohms come from? Where does 75 ohms come from? Why do we have these things? Well, it's a little bit of it's like that old apocryphal story about why our railroads a certain gauge is because of the rear end of Roman war horses was so wide and they had two, so it had, you know, it's a little bit true, but not quite. Here's the deal. Okay, back when coaxial cable was invented, the 20s and 30s, there are some interesting graphs out there, and they say, okay, different impedances optimize that cable, or back in those days they made it out of copper pipe with little glass beads and a copper wire in the middle. It optimized it for loss, or for power handling, or for ability to withstand peak voltage. Different impedances, different geometries have different characterizations. They found that 30 ohms is the optimum impedance for a coaxial cable to handle high power, and that was important for high power transmit. They found that 70 ohms is an optimum impedance to minimize the loss in the line for a variety of reasons, and I'm sure that EE267 or whatever they call it now will be happy to explain it to you with hyperbolic functions and all these wonderful things. So they said, 30, 70, can't have both. How about if we sort of split the difference here? 50 ohms had some geometry. It was common piping size, common wire size. They didn't have to come up with special tubings or anything else. Come on, fellas, come on right up here. There. Plop yourself down. These are the seats where I ask questions. Anyway, so the standard tubing sizes and plastic. Plastic was not always around. Polyethylene was not discovered as a commercial entity until the 30s. Okay, so we didn't have coaxial cable, and it was sort of a laboratory curiosity up until World War II. And then, oh my gosh, well, we learned how to make a lot of it real fast, real good. And if you've ever seen coaxial cable being made, that little machine that makes all the braiding stuff is real cool. And one of my projects when I was here, back in the days when dinosaurs roamed the earth and there was a building across the street and all this, was a guy named Charlie McDowell. And Charlie was doing a study on why, if you run the frequency up on coaxial cable, why does it sort of, the attenuation kind of go boing, 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 like this before, as opposed to just this. And after much back and forth, I was doing sketches for the department at the time, pen and ink, actual pens and actual ink. And I looked at a piece of RG58, and I said, okay, well, I've got two little pieces, two little pieces, two little pieces, two little pieces. Charlie came in and says, what the heck's the matter with you? He says, you're just not paying attention. You drew this as 2 and 2, and I said, here's the piece of RG58, look. And by golly, it was 2 and 2 and 2 and 2. He was expecting 1 and 1 and 1 and 1. All of his analysis to that point had been 1 and 1 and 1 and 1. And that's a certain geometry of little holes and conductive strap. And when he ran the numbers for 2 and 2 and 2 and 2, what did he get? Boing, boing, boing. So anyway, 50 ohms, standard tubing, plastic, we made coaxial cable. There's a good compromise performance for both power handling and loss, and we made so much of it you could buy it for pennies on the pound in the 1950s. Places like Fair Radio Sales, you get their catalog and stuff. You go to the warehouse, they would just have spools and drums and coils, and you just go in there and just haul it out by the truckload. And so once you get a de facto standard like that, there's just not going to be much difference. And 75 ohm cable became popular when cable TV became popular, and they needed to encircle the earth about 800 times with coaxial cable to get from the head end to your TV set. So we've got 50, we got 75 ohms. If you go through the catalog, there's a whole bunch of other really exciting impedances from down around 20 up to a couple hundred ohms. And they're used for very special purposes. But this is why 50, this is why 75. Okay. Nothing like a good war story. Okay, so we want to match our transmitter, our engine, to coaxial cable and the common loads so that we have a system impedance of 50 ohms or 75 ohms, whatever our system is designed for. So we're going to impedance match, all right? There are two ways to do this. Basically, one is resistive matching, where you use losses in your system to convert one impedance to another, or you can use reactive matching, which uses L's and C's. Resistive is cheap. Problem is you've got to give up some power, okay? But it's cheap. Sometimes you've got lots of extra power, and that's a good economic solution. As engineers, you've got to figure out where the sweet spot is in terms of your budget, your cost of goods, and cost of equipment, and all this kind of stuff. Sometimes a little resistive pad is just fine. When I was looking around here to see if we had like an intercom or something in here, you would see a dial on the wall, some places where that would change the volume of the speaker for a paging system or something. Those are resistive pads. And so basically you would switch in different combinations of resistors to keep the impedance happy out at the amplifier, but then it would dissipate some power and drop your audio level. 50 ohm attenuators. That's another perfectly good example of something that's a impedance matching. If you're going to measure a filter or something like that, and you go to, say, Hewlett-Packard / Agilent application note, you'll always see the generator with like a 20 dB pad in between the generator and your filter. Why not hook it right up into the filter? Well, the filter's impedance, it may go all over the place, okay, which would uncalibrate your generator. Generator wants to see 50 ohms, 50.0. That's where it's calibrated for. So by putting an attenuator there, any reflected power back from the filter, any changes in its impedance are minimized, and so the generator stays calibrated. Parallel and series resistors are also a very common way of matching an impedance. Hams often see, and if you deal with the military or EOCs, public service type of things, wideband antennas that look like a folded dipole. They look like two pieces of wire connected together at the ends, and they're stretched out like a common dipole. But up in the top wire, there's this thing. There's this magic thing. What's that magic thing is a resistor. And what the resistor does is it swamps out some of these wild impedance changes that you get as you move your frequency around in a dipole. And so it burns up some power, sure, but also it keeps your impedance right in the sweet spot for transmitters so that your transmitter is happy and you get this effective signal. If you are the system designer, the comm system designer, you've got to take that into account. It's going to burn up about half of your power at some frequencies because the antenna impedance is very high, but your resistor impedance that's about 600 ohms will burn up some of that power. Well, can I still get a good signal over to the other side of the state if I'm burning up half my power? Well, if you've got the budget, you just buy a 6 dB bigger transmitter, problem solved, okay? It doesn't always work for the hamsters, but that's why you use this kind of an antenna. Another type of resistance matching is really long runs of old coax, okay? Sometimes a really good dummy load is about a 5,000 foot spool of coax, and it'll happily soak up all of that energy. You shoot the RF into it, it'll run for a mile, hit the other end, all the way back, nothing makes it back. It's just the same as if you had a perfectly good dummy load out there. Okay, so a really long run of coax will lower your SWR curve. If your antenna looks like this, and you run it through 300 or 400 feet of RG58 at 14 megahertz, your SWR curve will wind up looking like this when it gets to the shack. And your antenna looks great, except nobody can hear you, okay? So when your antenna SWR at the antenna goes like this, but by the time you get into the shack, it's like this, it's bad, okay? You're shooting up all of your power into losses. But a really long run of old coax or small coax will definitely act as an impedance matcher. Here's another common impedance matching technique. If you're into designing amplifiers or circuits, that sort of thing, the transformer is a very, very effective way. Get to know about ferrite, F-E-R-R-I-T-E, ferrite devices, ferrite cores, all these kind of things. They're wideband transformers, use these things like candy. They're really good. If you can get good at being a ferrite designer, employers will look kindly upon you. And I might add that I've gone to a bunch of trade shows and like the International Microwave Symposium and stuff. And when the ARRL was there with the ham radio booth, I get all kinds of senior level people coming to me. They say, "Oh, we're so glad you're here. We need more hams." Why do they need more hams? Because you get an experience level that somebody that doesn't do systems, communication systems, it takes them years to get. Okay, so when they see ham radio on a resume and no felony convictions, okay, you've got a leg up because they know you've been out there. They know you understand a power supply is a critical part of a communication system. You know about the ionosphere, you know about coaxial cable, you know about connectors. You can't simulate this stuff, okay? Nobody has ever made a contact from LT spice to LT spice, ever, okay? It's all got to go through transmitter and antennas and everything else. So, learn about ferrites. Ferrites are very good, lots of new material about it. Remember we talked about impedance being the ratio of voltage and current. What does a transformer do? It changes the ratio of voltage and current. This is an impedance converter. Yeah, we call it a transformer, but what it really is it changes the ratio of voltage and current. So it's a very good impedance converter. Broadband transformers, just showed you the transmitter. Audio and modulation transformers. There's actually a thing called a modulation transformer, and we used to do that back in the days of mercury vapor rectifiers and things like that. AM transmitters, if you go out and you find, is KTTR still on AM? Yes, and they have a little...
This is not always working on AM.
Okay, yeah. You go out and you find the doghouse where, you know, this little tin shack out there, you know, and there's a bunch of big tubes in there. One of them is going to be, well, there used to be tubes. Now it's all solid state modules in a thing about the size of a refrigerator. And where's the fun in that? There isn't any, okay. But you used to see this big modulation transformer in here. And so you would pump your audio through this transformer into the high voltage that fed the tubes, and it's called plate modulation. And the plate voltage would go up and down with your voice, and so with the power that came out of the transmitter. Modulation, if you're into high-end audio, okay, the transformers that are used there are very, very wideband. Audio goes from, you know, 20 hertz up to 20,000 hertz. How many decades is that? Okay, can you imagine a radio system that went from 20 kilohertz to 20,000 kilohertz? That's a ratio of 1,000, okay, 3 decades. So audio modulation transformers are definitely broadband. Powdered iron cores are another technique that's used similar to ferrites. And basically here you go, okay? The voltage in the secondary to the current in the secondary is the impedance of the secondary, and similarly for the primary, here's your N squared. N is the turns ratio between primary and secondary, and that's the secret for how you do impedance transformation or matching with the transformer. And it goes by the square of the turns ratio, 2, 4, 3, 9, etc., etc. There'll be a quiz. Here's an example of a broadband transformer that uses a powdered iron core. This is out of the ARL antenna book, and W2VJN designed this. It's got a trifilar winding of bare wire. You can see these 3 wires are all together, and they are connected through this relay in various combinations. This one can be set up to do 1-to-1, 4-to-1, 9-to-1, or 16-to-1. And so I can take this out to my field day site, for example, and I can put up my antenna, and who knows if it's going to work or not. It's field day, so it's very temporary. It's something out in the field. So you switch this relay back and forth until you get an approximate match that your transmitter can handle. So this is a broadband transformer. This is a powdered iron core. It's about 2.4 inches in diameter. It can carry a full kilowatt. Is there a question? No. Okay. All right, here's some schematics. The dots on there tell you the phase of the different windings, and basically that's a little picture of a broadband transformer. Okay, this is my pet peeve. Okay, you hear this all the time. Balun. What is balun? It's an abbreviation of balanced to unbalanced. Okay, and hams are really bad at using language in ways that it was not intended to be used, but we do it anyway. Okay, it's an abbreviation of this function. It is not a thing, it is a function. Any device that transfers power between a balanced system, in which both conductors are symmetric with respect to the system ground, it can be open wire line, free space dipole, that kind of thing, and transfers it to an unbalanced system, or vice versa, okay, where the conductors are asymmetric with respect to ground, coaxial cable, a single wire line, or a system. Anything that does that is a balun. Okay? The balun may or may not do an impedance transformation. There are designs of baluns where they do impedance transformations, and there are designs of baluns that are nothing but a wrap of cable around a ferrite core so that it blocks current from flowing back down the line. That's it. It's just a coil of coax, or it's a coil on a ferrite core. That's a balun, okay? You can do these funky little transformer-looking things where the wires are bifilar and they go through all these different holes in the transformer. That's a balun. You can have baluns where you take one feed line and then you hook that feed line to a halfway link feed line, and suddenly you can drive something that's 4 times the characteristic impedance of the line. That's a balun too. So there are lots and lots and lots and lots and lots of different types of baluns, but they do a function, perform the balance function. Okay, it's not a thing. And when somebody sells you a 6-to-1 balun or something like that, that's a balun plus an impedance matching transformer. And so that's called marketing, ladies and gentlemen. Okay, so, and engineers, it just drives us crazy, but that's what it is. It's just a convenient way of referring to this function. And you also have an un, which operates between 2 unbalanced systems, and that can be a typical transformer. There are different types of baluns. A current balun forces equal currents in its load terminals. That's the kind we like at antennas. Why? Because antennas respond to current. They don't care about voltage. The only thing that makes an antenna radiate is inconveniencing electrons to flow back and forth in a straight line. Accelerating and decelerating electrons, that's it. That's all. So it doesn't matter what the voltage is. So a current balun, which forces the equal current into the load terminal, is what you want. Voltage balun, it forces equal voltages in the terminals, but if the impedances in each of those terminals is not equal, the currents are not equal. And if the currents are not equal, you don't have a balanced system. There are different types of transmission line baluns. This is where you wind up coax and put some impedance on the outside surface of the line so they can act like a transmission line. And you've got basically 2 or 3 completely independent voltage sources to work with at the end. They're really fascinating. Transmission line baluns are really cool. You can have transmission line sleeve baluns, where you basically run your coax up, it comes through a hollow sleeve. The hollow sleeve is a quarter wavelength or half wavelength long, and so it puts a high impedance up at the feed point. I could talk about these for hours. You have ferrite bead coil coax, we just talked about those. Impedance transformer is not necessarily a balun and vice versa. Okay, all better now, thank you. All right, let's jump over to reactive matching. And this is what you're probably going to be more familiar with. It just means using L's and C's, okay? Network is a fancy name for circuit. I realize I'm in the network church here where we use words like network when we really want to say circuit, but we just won't. The most common is an L network. It's one L, one C, and it can convert one impedance to another, either low to high or high to low. You also see pi and pi L networks, which are basically L networks back to back, two of them back to back. The pi has a series component in the middle, and the T network has a shunt component in the middle. We'll talk more about these as we go. You can also make a resonant LC tank circuit, and you can move a tap around until you get the right impedance, hopefully. And if you've got the transmitter on, it's really exciting because you draw sparks. Okay, and this is how we set the Globe King on fire in 1978 in the basement of the Raleigh building and had it carried out into the street and let it burn. So we were fooling around with the LC tank circuits. And if you look back in the old QSTs, you'll see people taking a pencil and drawing an arc off the tank circuits, the LC tank circuits, to see how much power they were putting out, because that was before everybody had, that was before MFJ was invented and everybody had a power meter. So you basically just drew an arc off stuff and yeah, that's about right. Okay, networks can be high pass, where you've got series capacitors through the network, so as the frequency goes up, their reactance goes down and more signal gets to the output. Or they can be low pass, where you have series L inductors in series, and so as the frequency goes up, the reactance goes up and the output goes down. These reactive matching circuits, if they're not adjustable, are designed to work at just one frequency. They're called resonant networks for that reason, because the L and the C have certain values of reactance only at one frequency. If you change the frequency, the X of L goes up and the X of C goes down, and it no longer does the matching that you thought it was going to. Let's talk about the L network. L networks are everywhere. Two components, you can have an L and a C. They're also LL and CCs. They transform high to low depending on the orientation of the components. If you've got a high impedance over here and a low impedance over here, design your L network for it, and then all of a sudden you discover, oh, well, it's really lower over here than it is over here. You just turn the L network around and it works backwards. Series C is a high pass, Series L is a low pass. Let's have a look at a schematic, ladies and gentlemen. Here we go. For those of you into Eastern philosophy, you'll recognize the Smith chart has a yin-yang symbol in the middle of it. When I was 20, I thought that was really cool. Okay, it's actually still really cool. Each one of these Smith charts here, it shows you the white area, shows you where it is possible to match to the center of the chart. It's like knight moves on a chessboard. You get two moves. You go this way, and then you go that way. Okay, and I wrote a column in QST about L network matching, and specifically it talks about these kinds of networks. This one, here's your Z of the device, or the load, whatever, and you want to get it to Z naught, then you would use this topology right here. And there are 4 of these things, and they all match different regions of the Smith chart. If your Z dev is down here, and you have this topology, it ain't gonna work. So you've got to go someplace else. You've got to go over here, over here. See, you can just turn these things around, and suddenly they match. The Smith chart is a wonderful thing. You don't have to use it on paper anymore. But if you understand what the Smith chart is telling you, it takes the entire right half of the impedance plane, of the real part of it, and it takes the plus reactance and the minus reactance imaginary axis, and it squeezes them down into a circle. Okay, and so you get the entire half of the plane into this circle. And because of the mechanics of transmission lines, the neat thing about it is instead of using a rectangular graph and having these strange hyperbolic tangent kinds of curves, you get circles. And it's really, really neat. So spend a little time reading the hands-on radio stuff about the Smith chart. And you can also have CCs and LLs, and they do different things, and I won't even discuss what that looks like. But you can see there's 8 different types of L networks, and they can do wonderful things. Here's a pi network. It looks just like 2 L networks back to back. That's exactly what it is. And so you get an impedance at this midpoint called an image impedance. And it's, remember I talked about a gearbox, about how you convert one mechanical impedance to another. You know how if you have a gearbox, you can only make one gear so much bigger than the other, and the gearbox stops being efficient. If you have a little tiny gear and a great big gear, typically it won't do much power. Okay, so what you want to do is have several gears. Okay, this one has 3. It has 1 gear input, 1 idler gear, and 1 gear in the output. So it helps you, has a wider bandwidth, it can match a wider range of impedances. Used in tube amplifiers because tubes have an output impedance at RF of a couple hundred up to a few thousand ohms, depending on the size of the tube. Everything out here is 50. So to get from, say, 3,000 ohms to 50, if an L network, you could do it, but the bandwidth would be fairly narrow. You want to use this amplifier over a wide range. So you use a pi network because it can give you a wider range of match. I can also make a pi L network and put 1 more L out here. And I do that because it gives me better harmonic suppression, and that's an important FCC rule. You will learn about the FCC rule once you get out there and you start actually building things and you have to qualify and check and meet specs and all these things. Well, FCC rules become much more important than they were when you were a hamster. Okay, so a pi L network has 1 more out here and it makes your harmonics roll off. Here's a T network. This is typical of most antenna tuners sold today. If you go look in MFJ's catalog, you'll see approximately 8 times 10 to the 4 different models of antenna tuner. They all look like this inside. Okay, pretty much all except maybe 5. All right. What happens here is you get a series C on the input, series C on the output, and an adjustable inductor. If you get the expensive ones, it's a continuously adjustable inductor where a little wheel rolls along it. If you get the cheap ones, you get a switch, and so you can switch your tab back and forth. Why this? This is cheaper. It is cheaper to make 2 capacitors like this and 1 adjustable inductor than 2 inductors and 1 adjustable capacitor. Even though this is a high-pass network, so it doesn't do as well at harmonic suppression as if I had series Ls. That would have been an issue back in the day because amateur transmitters were less clean in the early days. Nowadays, they're all very good in terms of harmonic performance, and so it's not so important that you have series L to do harmonic suppression. It's just cheaper. You'll learn about cheaper when you get your first job, okay? Cost of goods, your boss will come to you and he say, you know, I realize that, you know, this gives us better performance, but customers really don't care about it, and it costs like $20 more for me to buy 2 roller inductors. And you know, we've got these little variable capacitors here, and you can just wire them up, and they only cost like $5. So would you do that? And you go, yeah, I'll do that, boss. Okay. So if you're going to sell 10,000 units a year and you save $5 per unit, you just paid your salary. Okay. You made your boss a happy guy. Okay. You won't see any of that. You'll get a new car. You'll get a certificate. Don't tell them I said that. Okay. All right. So that's what a T network looks like, and that's your typical amateur impedance matcher. It's also called an antenna tuner, a trans match, a Z match. There's about 800 different words for it. It all is an impedance matching device. This is a very cool app, W9CF. You don't have to write all this down. Just remember W9CF T-Network Simulator. And so this is a JavaScript thing. He works, I think he works at one of the big national labs down in Arizona. And so basically you give him your R of the load, the X of the load, and the frequency. And then you can tune the dials. Okay, this is like a Fisher-Price busy box for engineers. And you can see the SWR going up and down, and at the same time it will be telling you what the SWR is, how much power you're losing in dBs and percent. You can also click the auto-tune button, which is really fun. You can sit there and pop that beer. Did I say that? And turn on auto-tune, and this thing will go bzz, and you can watch it actually match this thing up. Really kind of fun. Transmission line transformers are also really cool. How many people here have coated glasses for glare suppression? Those are synchronous transformers. What they are is quarter wave coatings at certain frequencies that cause a series of infinite reflections that cancel the glare reflection off your glasses. That's all they are. We can use that at RF by making a quarter wave section, sometimes called a Q section, quarter wave transformer. If I want to change Z2 into Z1, I go find some coax with characteristic impedance that's the geometric mean of these two things. I cut it to be 1/4 wavelength long, and voila, I have Z1 over here. Only works at one frequency, okay, because that thing is only 1/4 wavelength long at one frequency, but it's got a pretty good bandwidth. The trick is to find the Z0 that's this value. This is real handy. Loops, for example, loop antennas have feed point impedances that are around 100 ohms, maybe 120, 130 ohms. If you want to get them to Z1 equals 50, then the impedance that you want here turns out to be about 75 ohms, which is handy. So basically there are a lot of loops out there for which you get a quarter wave piece of RG11, which is a 75 ohm, 72 ohm coax, depending on what manufacturer you purchased, and that makes a pretty decent match to your transmitter. Here's another secret. If your SWR is 1.5 to 1 or less, it's fine, okay? You're not going to get very much extra loss because of that. It's not going to reduce your SWR bandwidth a lot. It's not all that bad. People obsess over getting SWR down to 1 to 1. It's 1.5 to 1 or less. You're good at HF. Okay. You can also use that surplus hard line that you got from the cable TV guy for giving him switch type, and it gives you all these tag ends of hard line, but it's 75 ohms. Ham stuff is all. It's all 50 ohms. I can't use 75 ohms on 50 ohms. I'd have an SWR of 1.5 to 1. Oh my God. So what do? Okay, if you're going to use it on one frequency, you put in 2 little 12th wavelength long pieces, and the sequence of reflections that are set up at each one of these junctions. You get an infinite sequence of reflections. It's great math. If you like math, this is for you. And all of them cancel this line. So the wave comes in and it starts going dingy, 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 ding. And by the time it's all over with, by the time you get 10 or so cycles in there, this thing thinks it's at 50 ohms. It's a really cool thing. So you can use 12 wavelength transformers, quarter wavelength transformers, and you know, you go talk to one of these older RF engineers, they'll have a whole folder full of interesting synchronous transformer designs. Only works at one frequency or one band, but it's pretty handy. Okay, antenna feed point matching. These are structures that you build at the feed point to do this matching. You can also use transmission line techniques. They do require adjustment at the antenna, which can make for some interesting moments at the top of the tower when you're leaning out there to get to the matching section. Don't ask me how I know this. They are also one band matching. Here's the delta match. This is the original. Okay, 600 ohm line, okay? Well, the line's going up to the antenna, and people said, well, I'm just not getting enough power into this antenna. Why? Because the impedance at the middle of the dipole, let's not all see the same hands, okay? It's like 75 ohms at most heights. Okay, so 675, uh-oh, lots of SWR. Even for open wire line, that was too much. So they said, what are we going to do? Well, some bright guy said, okay, look, feed point impedance right here is 75. Feed point impedance out here is several thousand ohms. Someplace in between here and here has got to be 600. Ka-ching. So basically, they just spread the legs of the transmission line far enough apart until they got to 600 ohms. And the dimensions of this triangle for many antennas in common use at common heights for common frequencies for hams, it worked out well enough that this combination of 0.12 wavelength and 0.15 wavelengths made a decent match to 600 ohm lines. Now you got to be careful in ham radio. Once people get the idea that something works, they will latch onto it forever and ever and ever, and they will misapply it in more different varieties of situations than you can imagine. You all took your test and you all learned this number, 468. Okay, what's the wavelength? What's the length of a half wavelength dipole?
468 divided by the frequency in megahertz.
Sir! Okay, everybody learns that. Okay, it's never right. It's never, ever right, except for maybe one time in 1,000, okay? And so I decided I'm going to find out where this number comes from. It's not the half wavelength in free space, that's 492. Where does it come from? And so I started going back through the literature, and back and back and back, and I went to the very first handbook, 1926. It was not there. So someplace it had to appear. What was the deal? And so I went to QST and all this kind of stuff. Turns out that this guy, he wasn't even a ham, he was a commercial engineer in the early 20s, 1924, 25. He went to all of the ham stations in the Boston area that had good signals, and they had what was called then Hertzian antennas, which means a half wavelength long. Some of them were dipoles, some of them were inverted L's, some were monopoles, some were various combinations of these things. And he measured the length of each one of the wires and the frequency at which it was resonant. And then he went back and he made this table. Well, he came up with this certain fraction of a wavelength for these antennas tended to work pretty well on the frequencies that amateurs used during that time period, which was 80 and 40 meters predominantly. And if you work out the math, it turns out to be 468. 468 divided by frequency, megahertz gives you the length of a Hertzian antenna in feet. Well, it got into the literature, and after that it became stone tablets, okay, and it's carried through to this day. It never works. It never works. You get it up there, you hear these people, they say, okay, I want you to take this wire, and here's this 3-digit number. It's got 3 significant digits, so I want you to measure it to within 3 significant digits, and I want you to cut it to that length. And then they go, and then add a couple of feet. And you're like, what? So anyway, I went back and chased this all out. It only works for half-wave length dipoles on 40 and 80 meters that are installed over decent ground that you might find in New England at about 30 or 40 feet. Amateur radio started in New England. That's where a lot of its mythology came from. If it had started in Kansas, it would have died out in 2 weeks, okay? Because the initial range of these little stations was about 5 miles, okay? In Kansas, you wouldn't have been able to talk to anybody. And that's where the American Radio Relay League comes from, is a system, a network of being able to exchange messages from all these dinky little stations. Okay, so 468 over F, is a lie. Okay, so what I tell people is start with 490. It's for sure going to be too long. Put the thing up, measure the resonant frequency. Oh, it's too low. By how many percent is it too low? Okay, shorten it by that number of percent. Problem solved. Okay, but don't look for a magic number. Okay, anyway, I feel better. Nobody told me this when I was in school. I had to learn this part. Okay, T-matches. All right, well, they decided the delta match was kind of unwieldy, and we started putting these things in called beams, where you had a rotary beam. Back in the day, they actually used wood, and they would have big disputes over whether it was better to varnish or boil in linseed oil. You know, it's one of these things. Okay, so they still had the open wire transmission line. It was all a balanced system. How do I match this transmission line to this thing? Okay, well, somebody said, well, try the delta. Well, that doesn't quite work. This works better if we flatten out that triangle and make a transmission line piece out of it, essentially. This is a very shorted transmission line, and they were able to get the same effect with series capacitors, series reactance. Okay, so that's what a T-match is, and you still see that at VHF on occasion. This is far more common. This is a gamma match, okay? It's 1/2 of a T-match, and it works because we now use DC ground elements and coax for the transmission line, where this outer surface is at DC ground. Okay, so basically this is an RF neutral point here, low voltage. So we can do away with this other half. We can just put that one capacitor here with a little piece of transmission line, tweak in the capacitor, maybe move it back and forth a little bit, and voila, we have a match. It typically looks like this. Instead of an actual capacitor with the adjustable plates, it's typically a tube, a piece of aluminum tubing with a plastic insulated center conductor in the middle. It almost looks like a piece of coax in there. And so you move this, move the distance, you move the shorting bar, and you can move this thing in and out. And all three of those adjustments, boy, do they interact. But when you get it done, it works very well. That's a gamma match. Beta match. What happens, okay, if this is an RF neutral point in the middle of my driven element, what I can do is I can cut that, okay, and I'm just going to put an inductor across this. This is an inductor. It's called a hairpin because it's a long parallel chunk of shorted transmission line. It's less than 1/8 of a wavelength, so it looks like an inductor. And so you make the feed point impedance of this thing a little bit capacitive, just a little bit by making it too short, and then you add this inductor across the feed point, and that gets rid of the reactance and transforms it up to 50 ohms. This is really an L network. The C is supplied by the driven element, and the L is supplied by the beta match. So this is really an L network, and then people put a 1-to-1 balun here to isolate the outside surface of the cable from this insulated driven element. High gain beams use this. It's a fairly common technique. Okay, that's enough. I've sprinkled my wisdom all about the room, and then you're going to go check it. Like everybody has to on the internet these days. You can't trust anybody, not even me, maybe not even especially me. So where do you go to get the real stuff? Okay, ARL handbook, ARL antenna book. The antenna book comes with some software. Transmission lines for Windows is a marvelous program by Dean Straw. It will compute all sorts of things like what's the input impedance if I've got 43 plus J20 over here and I've got 50 feet of RG213, what's my input impedance? Solved. How long is a quarter wave piece of RG174, et cetera, et cetera, et cetera. TLW comes with the book. Match is a great little program for designing L networks. There's a bunch of other stuff in there. This is a good book if you want to learn more about antenna tuners. It's by W1ZR. He surveys all the different types of commercial units, tells you how to use them, tells you why it's better to set them one way and not another. You can make a T-match tuner. Their tuning is so wide that they can essentially tune up into themselves. And all of us have done this. You forget to connect anything to the output, and you fool around with it, and sure enough, the SWR comes down, and you're happy as a clam until you go, what's that smell? And so he talks about that. The ARL Online Archives. How many ARL members do we have here? Good. Okay. It's people say, oh, it costs so much. Listen, wait till you start paying your IEEE dues. Okay. Online archives go back for 100 years, and all that stuff is in there. And a lot of this stuff that you will see in your books, a lot of it was put in one package by this guy named Terman back in the late 30s, and many engineers have a copy of Terman, and he was a Stanford guy. You remember? Yeah. Anyway, classic stuff, and the physics hasn't changed at all. Okay, so all that stuff's in there. Good stuff. The ham radio magazine was also very good. It's searchable. It's not archived, but if you ask around, you can find somebody with a CD set and get it. I think, does the Radio Club still have all the ham radio magazines?
Some of them.
Some, yeah. I used to read those just by the hour, okay? The Antenna Compendium, Volume 1 to 8, and there's this column by this N0AX guy at QST. Actually, the column is coming to an end in December, and I'm finishing with Maxwell's equation. So we shall see how that goes. More good stuff. Did that stuff about transmission line transformers get your attention? There's some books out there. Jerry Sevick is the guy who really introduced these to amateur radio. He worked for RCA and other big defense and industrial contractors. He was a communication system expert. This book is really good. Walt Maxwell was another one of these proto designers, you know, and he got so tired of hams using the word SWR and other things improperly that he said, look, and he wrote this 7-column sequence of articles in QST in 1974, and it just basically blew everybody's mind. So this has got turned into a book, any one of the editions. L.B. Sevick is a great guy. They're all dead now. What's the deal? So L.B. is a modeling expert, and if you can find a CD of his stuff, there are literally thousands of instructional articles and designs on antennas for you to play with. I mean, you can spend your whole life in there. Online calculators, RF Cafe, Microwaves 101. Microwaves 101 is by Jim Rauschio, HA3K. He is the CEO of Sonic, which is a major electromagnetic simulator, and he started off with an Apple II doing some simple calculators for RF stuff and doing some ham radio, and one thing led to another, and now he's got this amazing company. Microwaves 101 is really good. This is an older thing. You can get it off the CQ website. It runs on DOS, but it's like 150 little tiny calculators that you can run in the command prompt window if you want. Here's some textbooks. These are available online. They're in the public domain. Radio Engineering, Terman, get a copy. Radio Antenna Engineering by Port, also very good. Antenna Fundamentals chapter of the ARL Antenna book. We pulled all this kind of stuff together into a summary that helps you understand what antennas are. So I covered a lot of ground. Everybody's got that deer in the headlights look. I'm thankful for your attention. I'm so pleased to come back here and stand up here where I was tormented for so many hours and torment somebody else. It was great. Thank you so much.
Thank you.
Questions? Yes.
I have a quick question. When's the next antenna book coming out?
I keep pestering them about that, and they haven't said, but it'll probably be within the next couple of years.
Okay, I need my hardcover, so they're sold out, and I need my hardcover.
There you go. The 2018 ARL handbook is a major rewrite this year. Lots of SDR stuff. All of those receiver transmitter chapters have all been redone. It's a big deal, and so now we're going to do that for the antenna book too. Questions or comments? Okay, thanks.
Thank you.